Okay, that's fine. Let's start our session for today. And please, first of all, we have here live Q&A. You can put your question. If you have any question during the session, you can post it in the Q&A panel. And then by the end of this session, we are going to answer these questions. And please feel free to ask any question about anything that we will discuss today in this session that you don't feel it's clear enough, or maybe you have any other questions related to the machine learning field, that all of these questions are fine. And this is an opportunity to have this kind of discussion together and to have mutual benefit of this session today. So first of all, let me introduce myself. My name is Osama Abdelhamid. I'm a solution architect. And I'm working as a software team lead for long years now. And also I'm working in the machine learning field and the deep learning field. I worked as a mentor in Udacity for the deep learning and machine learning. And today in our session, we are going to continue the first session that we started last time about the Azure Machine Learning Service and the different capabilities that we can utilize to build effective AI models. This is actually a world of endless potential, and we can build a lot of things which solving real problems which we face every day. And as you can see, the field is very emerging and it's very demanding. So there is a great potential here. And I hope this session will give you a way of thinking about the machine learning without having a lot of complications around the keyword here. But as extension for our discussion last session, we actually going to explore more and dive more into the details of the Azure machine learning, okay? And we will see two demos, real demos, about how to build this practically in Azure. But first of all, let me give quick presentation. It's not quick because we have a lot of topics to discuss actually here, but we will try to go quickly through the topics in the presentation to allocate more time for the demos. So first of all, we talked last time about the machine learning pipeline and the machine learning workflow. We are going to recap again. In general, when we are talking about the typical workflow in the machine learning, we have common steps. We are starting from collecting the data. This data we have to collect the data which is relevant to the problem we try to solve. This is very obvious, and we then start by looking into this data. This data might have issues because it's a raw data. We collect it from the wild, from the real world, okay? It might be data collected from patients' records, might be data collected from manufacturing lines, might be data collected from Amazon about the different things that people usually purchase from the site or so. This kind of raw data almost needs pre-processing. So we start with the cleansing of data, looking into the different issues within our data, and start apply the proper pre-processing steps, which helps us with making our data ready for building the desired model. So in the second step and the third step, we have the cleansing of the data. And we have also the transform of the data. We might need to take a text data, and this text data, computers doesn't understand text. So any model has to be numeric. We have text data. If we feed this text data to any machine learning model, it will not be suitable. It will not be useful. So we need to, in all cases, to transform this data to numerical representation that our machine learning model can understand, our computers can understand during the training phase. Then we go to the training phase where we are trying to fit a model to this data. what does it mean fitting a model to our data? Actually, when we have inputs and corresponding outputs, we believe that this data which we have, there is like underlying relationship between these inputs and those outputs. And we try by fitting a model to this data to find this mapping, this representation by training that model using a specific algorithm. This algorithm can vary based on the kind of problem we try to solve. And that point we are going to discuss in the next slides. Then after we have a trained model against our data or which is fitted to our data, we need to evaluate that model and score the model to understand if this model really will help us with solving our problem or no, it's a poor model which doesn't help to solve the problem. Then after the evaluation, to understand the goodness of this model, if we are fine with that and we feel really that model can predict the new data and the unseen data in a good way, we move on with the deployment of this model. So other people, the target audience or the public users who should get benefit of this model can use it. So we can deploy it as a web service or as a REST API where I can expose this service to users through a mobile app or web application or any other interface. This is actually the common steps. You will find these steps everywhere you go through the machine learning in different shapes, but eventually it's the common steps that you will find all the time, specifically if we are talking about the supervised machine learning. We talk about algorithms. In the algorithms, we actually pick the right algorithm as per the problem we try to solve. We can make a nice categorization for our algorithms into the following. We have regression, we have classification, and the regression, actually, we try in the regression to predict a numerical value. It could be, as these examples shown here in this slide, it could be the temperature, simply. It could be a house price, product price, a consumption of petrol for the cars. It could be the utility usage of the new building, okay? It could be many other examples which eventually try to predict a numeric value. And then we have the classification where we have binary outcome or categorical outcome. We try to answer yes or no, cat or dog, patient or not, diabetic or not, has a specific disease or not. We might have also multiple categories if that question could be classified as something related to Java, could be related to .NET, could be related to PHP. This kind of different categories where we have maybe 10 or 100 categories, and we try to classify the input, map it to one of these 100 inputs or outputs or 10 outputs. This is the classification. We have very discrete outcomes where we try to establish the mapping between the inputs and the outputs in that classification setup. Like in this example, we have spam or not. If we have email, we want to classify this email, maybe it's a spam or not. Maybe this is specific customer based on a specific characteristics or inputs will buy the specific product or not. He will stay with us as a customer, or maybe he will leave us. The movie rating, if I have movie rating from 1 to 5, what the expected rating for this movie, given that I can feed the model with the different characteristics about this movie. And also maybe the genre, the actors, the type of this model, the director of this movie, and so on. There is a lot of characteristics we can think about in reality, which could be inputs for such case, where we need eventually to map this to the final outcome, which is the rating in that case. If this movie rated as 1, 2, 3, 5, maybe. Depends on the scale or the rating scheme you are following. And the third classification here in the algorithms, we have anomaly detection. The anomaly detection here, we try to predict the rare events. We have some rare events. It could be fraudulent transaction in the money transactions in the banks. We want to identify if this transaction is fraudulent or not. If we have, for example, manufacturing line, and we want to predict automatically from the products or the components we are producing from this manufacturing line, if these components, these produced components, has defects or not. These kind of rare events we can predict and identify through this domain of anomaly detection algorithms. We have many techniques where we can find out and actually highlight these kind of rare events if we train a model with enough data about that specific problem. We have also clustering. In the clustering, it's a kind of unsupervised learning, which means we don't have specific labels predefined in our data, but we have raw data, and we are trying to understand what could be the hidden insights within this data. And eventually, in the clustering, we try to group the items based on common similar features. And as an example, we can think about understanding the behavior of customers in their purchase style based on the data that we have. So if we collect enough data about some stores and maybe for 1 or 2 years, and we, after collecting this data, we start to study what is the common features, what is the similarity between those customers. Can we segment those customers based on their purchase style, based on a specific pattern in how they are actually more interested to specific products than others? And finally, we have the recommender systems. The recommender systems, it's a very common thing. You can see it in Netflix, you can see it in Amazon, you can see it for any website where you have some products and you visit this site, you are searching for a specific product, but underneath, usually you can find, because you are interested in this product, we are recommending to you similar products, okay? These kind of recommendations, you can see it also in the movies. When you open Netflix, it's measuring how this person can be more likely to watch this specific movie or to buy this specific product, okay? And this is a very common field also under the umbrella of machine learning algorithms. What does it mean to train a model? When we say training a model, what really does it mean? We try to learn specific parameters. Our model, based on the given data, try to learn specific parameters. These specific parameters is a configuration variables which is internal to this specific model. The value here for this specific parameter will be estimated from the data, which means that if I'm trying to train the same algorithm against a different data set, the values for the parameters will be estimated differently, okay? So the parameters here, which the model try to learn to establish the mapping or the relationship that we talk about in the first slides, it's very specific to the model, and it's basically dependent on the data, the data we feed to this model. Then after we go through the data to fit it to our model, we actually learn the right parameter values, which could be a representative of this model. So you can imagine that your model simply is a line, and we try to fit this line against different data points in the space. This line has slope, okay, and you can think about this slope as a parameter. This slope of the line is a parameter. What is the best slope for this line to be fitted to our data? This is a kind of parameter value we try to estimate or learn from the data. Okay, and actually here also we have another terminology which is very important to differentiate between model parameters and model hyperparameters. If we have algorithm, we try to set up this algorithm to train a machine learning model. Every algorithm has its own internal parameters. We call it hyperparameters. These hyperparameters is a kind of setting, configuration setting for the algorithm. And we can play with the hyperparameter values to tune our model. This kind of hyperparameters tuning, we do it always before starting the actual training. So it's something we cannot learn from the data. We cannot estimate from the data. It's a configuration setting for the model. We do it before the training. But once we are done with specific hyperparameters, which is representing our model, we start the training. During the training, we estimate the parameters from the data. This is a major difference here that we have to understand, because when we say parameters, you understand this is the learned parameters from the data. When we say hyperparameters, you will understand immediately that the hyperparameters mean the configuration settings of the model, which could be different from one algorithm to another. If you are using, for example, a naive Bayes or support vector machines or decision trees, you will find for every one of these algorithms, you have different hyperparameters that you can tune it to get better results. Okay, but within each model, if we use different algorithms, you have to learn from your data, because eventually this trained model will be used to predict the unseen data. If we cannot capture in this model the right parameter values, which do the right mapping between the inputs and outputs, this model will not be useful, and even, at the end we cannot use it for solving our problem. Okay, this is a very important definitions in the machine learning. Now, how Azure Machine Learning Service can help us with this? In Azure Machine Learning Service, we have a set of Azure cloud services, okay, and we have Python SDK. These kind of cloud services that we can use to build machine learning models, train them, using them for the prediction. You have very handy services in Azure where you can do your data science project in a nice way, in one place, without any need to have heterogeneous tools in your project. So that will help you actually to have good results, find the right compute for your machine learning experiments and so on. Plus, you have also the Python SDK, where you might deal with complicated problems that needs advanced development to build your own model. So also you have this kind of flexibility, because I can go and use the Python SDK to build my models, to train the models against different frameworks. And when we say against different frameworks, we have a lot of libraries out there which we can use it, and there is no restriction in Azure Machine Learning which framework or which library you decide to use when you build your model programmatically. Okay, so this combination will enable us to do the steps that we talked about, to prepare the data, pre-process the data, build the models, train the models, then after that manage the trained models, track the experiment. The experiment here means I'm training my model against the specific data, and that is called experiment. And because the machine learning field is experimental by nature, we call this experiment because every time I need to repeat again and again my experiments with this specific model to tune, to change, to test and evaluate. And this is usually a very iterative process. So every time I submit my machine learning pipeline for execution, this is we call it a run, and it's running within the boundary of an experiment. Okay, that's why we say here one of the nice things is to track experiments, and eventually, if we are fine, as we said, we deploy the models. Okay, deploy the models to get the benefit of the final outcomes, make the predictions and solve the problem we try to solve. Okay, the machine learning pipelines actually is a workflow. It's steps. Okay, could be sequential, could be running in parallel. We have both cases actually, and each step is a specific task you try to achieve. You can think about the steps as follows. You start with cleaning the data, make pre-processing on your data. You can, after that, make transformation on the data. This is the second step. Then train the data. I need to split the data to training data set, and test data set. Then feed this data into a model to train, and then evaluate or score this model. And eventually, the last step will be deploying this model as a web service. Okay, this is a very common steps and tasks within this workflow, which compose the pipeline. In the pipelines, okay, we have two types. It could be a training pipeline, and it could be prediction pipeline or inference pipeline. Okay, if you look here, we can summarize by see this components or these building blocks. We have prepare the data where we expect these kind of actions or steps for the data pre-processing, like normalization to have your data on a common scale, transformation to transform the data from specific format to another. You can also make a featurization to make manual picking for your features, if we are talking about the traditional machine learning models. And you have your data on the left side, you ingest your data to make the pre-processing required. Then you push it to build and train the model. And the last block is deploy this model somewhere to get the predictions. Okay, if you look here, you can see that we start by make the processing steps. Then we go to the build and train models. Then we start testing our model, validating our model. This testing, as you can see, it's iterative. Okay, once we are fine with the model validation and we get the tuned model, which could be the final model in this case, we push it to a deployment step where we can host this model in a specific production environment to serve the customers. Okay, you can see here when it comes to evaluating our model. Okay, in the evaluation part, we have very common metrics for the evaluation. These metrics will also be different based on the problem. If we are talking about classification, we already discussed the difference between classification and regression. So we'll focus here in the classification first. In the classification, we have something very common called confusion metrics. As you can see, this confusion metrics, it's really a matrix where you can see here the predicted values, okay? And we can see here the actual values. Suppose that we are predicting cat or dog. We give to our model an image, okay? And this image has single object. It could be a cat or dog. And I want to the computer, my model, to be trained to recognize the cat, okay? In that case, if I consider the right classification is cat, I will look here to true positive. This is TP, is true positive, okay? Why it's true positive? Because it's matching the actual value, or the predicted value is matching the actual value, okay? And we have also the true negative, where if we said it's not a cat, okay, yeah, it's predicted as not a cat, and it's actually not a cat. This is the true negative, okay? So in both cases, the classification is correct, okay? But in the red areas, we have false negative, okay, and false positive. The false positive, where we actually try to say this is, we call it type 1 error, where you have a predicted value which is positive, but it's actually false. It's not positive. But your model get it wrong. There is another type of errors which is false negative, FN, here on the left bottom, which is your predicted value is negative, but it's actually positive, okay? Maybe this is a confusion matrix because it's at the beginning it might confuse you, but this is a very effective way to measure the efficiency of your classification model. It will be clear here. If you notice, we have here a cat, and our model predicts this image as a cat. So it's a real cat, and it's predicted as a cat. Here we have a dog, and the classification of our model, it's not a cat, which is correct. We call this true negative, okay? And here we have false positive, okay? This false positive, okay? You are a cat. This is a dog, but the model predicted as a cat. That's why we call it false positive, okay? And finally, we have false negative, which is you are a dog, okay, but it's not a dog. The expected outcome to be a cat, so it's false negative, okay? I think this image is quite nice to explain the idea of the confusion matrix. And as you can see, we call this kind of problem binary classification because it's 0 or 1. It's cat or dog, okay? So this is the idea. We have also in the classification from this confusion matrix, we have other nice metrics which very common in the classification problems, like accuracy. In the accuracy, we simply measure the accuracy by counting all the correct predictions and divide that by the total predictions. So suppose I have these numbers where I have 6 true positive and 11 true negative. We agreed that both of them are correct, predicted in a correct way. So if we sum up this, we come up with 6 plus 11 in the numerator, and we have false negative and false positive, which is predicted in a wrong way, okay? And we actually sum up all of the predictions and divide the correct predictions by the total number of predictions. The percentage we get, we call it accuracy, okay? We have also precision. This precision is out of all the predicted values, all the predicted positive values. In that case, we out of all images predicted as cats, how many actually is cats? So we have predictions which is actually positive, it's a cat, divided by the total predicted as cat, okay? So if we look here, this true positive, it's predicted as a cat and it actually is a cat. This false positive, it's not a cat. If you look here in this image, it's actually false positive. Here you are a cat, but it's not a cat, okay? But it's predicted by the model as a cat, okay? We call this false positive. We take this true positive and the false positive and divide the predictions, which is actually positive in this case, by the total predictive positive, okay? We get a percentage. We call this percentage precision, okay? And then we have the recall. What is the recall? This is the recall power of the model. Out of the actual cats that we have in reality, okay? How many predictions are cats? So our model predicts this number of cats. What is the total of the actual cats in total? And of this total, the model was able to recall, to predict those as cats. So suppose you have in total in your data set 100 images of cats, and the model was able to correctly classify 90 of them. So this means that 90 by 100, which means 90%, your recall power, the model recall power is 90%, okay? These kind of metrics is very common, as we said, and we have something else called F1 score, okay, or F score in general. And this F score is simply a function of the recall and the precision, where we try to get a matrix which is making a trade-off between the recall and the precision. This is also another matrix, and this is all about the classification in general. This is a common matrix. And we have also the regression. In the regression problems, which is predicting a numeric value, as we said at the beginning, we have a very common metric called root mean square errors. This root mean square errors is, you know, when we try to train our model will predict a real number, will predict a numeric value. It's the price of the car, for example. This price of the car, which is predicted by our model, when we compare it to the actual price, there is a difference. This difference, we get the difference by subtraction here, okay? And we go through all the instances we have in our data, all of the cars, okay? And then see what is the difference across all the cars, okay? We are evaluating between the value we predicted for the price against the actual price. Then this differences across all the cars in our evaluation set will be squared, okay, and summed up, okay. Then we divide by all the cars we go across, and then take the root square, okay. We call this root mean square error, okay, because actually we take like a mean or average, okay, because if you notice here, we divide by the total number. We take the difference and sum up the squares, divide by the total number, and then take the root square, okay? This is a very common also metric in the regression problems, okay? This also summarizes the RMSE, where you have this line, you consider this red line your model. And this diamond, blue diamond is your data points. Imagine that the data points is the car. And this car price, this is the car price. When we compare the delta or the difference between each car here and the line which is representing our trained model, we notice here the difference or the gap is the error between the predicted value and the actual value. This error, when we go and sum up these errors, as we said, divided by the total number of cars or data points, take the square root. This is your RMSE, and it's a great way. And we can see here this square of the errors between the predicted price or actual price is needed because we don't want the differences to cancel out, because if you notice here, we have some cars above the lines, we have some other cars under the line. So the things which is under the line, if we leave it without taking the squares, that will cancel out the other cars or the other data points above the line. And also there's another reason for have this kind of squares. Sometimes we need to penalize the trained model if he make mistakes or this model make big mistakes and so on. But this is another topic because that will take time. Okay. I think that will summarize all the evaluation metrics that we can expect. Here we said there is another type of the pipelines, we call it inference pipelines or prediction pipelines. If you notice here, we bypass the second step. We bypass here the build and train models. We try to predict, that's why we have our trained model, so we don't need to go through the training again here. We just do some pre-processing steps or preparation for our data. Then we take this data and serve it by our trained model to get the predictions. This is the inference pipeline. If you notice here, in Azure Machine Learning, there are many frameworks supported. You have Cafe 2, you have Chainer, you have MXNet, you have PyTorch, you have Keras, you have TensorFlow, you have scikit-learn. There are many frameworks and libraries which is supported. You are not logged to a specific framework when you work on Azure machine learning. And if you notice here in the middle, we have open format. This is open standard format called ONNX model. What is ONNX? This is a kind of open standard format. It's an open source project, okay, where different companies, big giants like Microsoft, Facebook, Google, need to come up with open standard format, which can be used across the different popular frameworks. So I can train a model in PyTorch, and this model could be saved eventually as ONNX model, and that format will be understood, will be parsed correctly when I move it to another framework. So for AI developers, it's a great way of having this. It's something great actually, because you are not restricted to specific framework. You are not restricted to specific library. The AI developers in the same team or across different teams, we might have some people who are expert in PyTorch. We might have some people who are expert in scikit-learn or TensorFlow or Keras, okay? There's no restriction between them because I can train a model and give you the ONNX format where you can import that model and continue working on this with your own different framework, okay? And this ONNX model could be actually deployed as a final trained model to different compute targets here, like maybe Ubuntu virtual machine or Windows virtual machine or Azure Kubernetes service, or maybe to a handheld or mobile device, okay? There is no restrictions here. There is a lot of nice things you can do with this, okay? If you notice here, this is summarize the high-level picture, okay? This is what we call it MLOps or DevOps for machine learning, okay? It's a new field where we try to simulate or to implement the DevOps practices in the machine learning field, okay? If you notice here, it summarizes a lot, like you have the train and test of the model, then you get the trained model and register this model in your machine learning workspace, as we will see now. And this could be encapsulated as a Docker image, okay? This Docker image could be pushed to a specific repository where you can make it shareable to others. And this Docker image, which is encapsulating your trained model, could be then deployed to Azure App Service, could be deployed to AKS or Azure containers instances and so on, okay? And deploy the service and monitor and build your model. Here we started from here actually, so you can build your model in any favorite IDE. You can use any specific tools as an AI developer. You can use Jupyter Notebook. You can use VS Code. You can use other IDEs. There is no much restrictions here, as long as this kind of tools, it's part of the common tools used in the machine learning field, okay? You have PyCharm, you have many other ways of building your models. You are not restricted really to a specific IDE or a specific tool, okay? As we said, when it comes to deployments, you have different compute targets. These compute targets, or we call it deployment targets, okay, could be for development and testing, could be Azure container instances, could be Azure Kubernetes services, if we are talking about production environments. It could be even Azure IoT Edge. If you have IoT Edge, which is fixed somewhere in a factory or a specific place to do specific task, you can deploy this trained model in that IoT Edge to do a kind of artificial intelligence task or predicting something maybe related to the air pollution. You can imagine that if I have IoT devices which is fixed somewhere around the city to detect or predict maybe based on the current reading or the collected readings across the day or for several days, what could be the expected pollution level for the air on the next day or the next hour, something like that. You can imagine in the real world, which is suitable to the case. Okay. Now we come to the step of the demos. What we expect in the demos, we have 2 demos today. We have the first demo about the heart disease reduction using the auto machine learning, okay, or auto ML as we call it, okay. And we have another demo about diabetes classification using a dataset from Kaggle called BIMA Indian diabetes dataset, okay. This in the second demo, we will explore the pipelines and the tuning of the pipelines and so on, okay. So let me switch to the Azure Portal. If we switch to the Azure Portal to start the demo, 1 second. Yes, here we go. Let me check that this is shown here in the live. Yes, okay, great. So this is our Azure Portal. We started from here. I have here, I already created a resource group. Inside this resource group, I already created all the required resources. Specifically, I created the machine learning workspace, which we already demonstrated in our first session. And then I have the machine learning workspace. We call it machine learning service here, as you can see, the name of the resource, okay? And then we launch Studio. This is the machine learning studio or the workspace where we have everything related to the machine learning experiments and work that you can do, okay? As we will see now. Here, this is your machine learning workspace. And as you can see, you have 3 main sections on the left side. You have the author section, you have the assets section, and you have manage. In the author section, you have notebooks, Jupyter Notebooks, you have automated ML, which we will talk about now. And we have the designer where you can build your training and inference pipelines. Under the assets, what is the assets? Assets could be your data set, could be the experiments you are running in the workspace, could be the pipelines you built in the designer, could be the models, the trained models, which you get it as a result of running your experiment or executing your pipeline. So here in the models, you can register those models to be saved in the workspace and used by others later. And we have endpoints. Endpoints is simply the web services, okay, we talked about. Under manage, in the manage, we have compute. What is compute? Simply, it's the virtual machine that we run our experiments on. To run experiment, to train model, to make predictions, everything like that will need a compute resource. We need a virtual machine. It will need maybe a cluster of different nodes if we want to scale. Okay, and we have data stores. Data stores is a pointer where your data is stored. Maybe we are talking specifically here about Azure storage service, where I have blob container, and this blob container will be the place where I'm going to store my data or my artifacts. Okay, so you can think about data store simply is abstraction of the data storage service that you use. But instead of dealing with Azure Data Storage Directory, with the Data Storage Solution Directory, you are not actually going to Azure Storage Service at all. You are managing your artifacts and your data right away from here within the workspace itself, okay? And we have data labeling where we can make some projects related to raw data that we want to ask some people, a team of people who can actually work on this data to correctly label each instance. So suppose you have 100,000 of images, but we don't have a specific labels for these images. We can hire some people, and here in the workspace they can access and start labeling the data set that we registered here and put the corresponding right label for each image or for each row of our data, okay? And the linked surfaces is simply integration with other Azure services like Synapse or Databricks and so on. This is still under preview. This is a preview service, okay? It's not generally available. This is a summary of the main components in the workspace. Now, to our model, to our demo, we said we start the hard prediction with automated ML. If we navigate to the automated ML here, you will notice that I can start from a new automated machine learning run, okay? That will take us through a wizard. But to do that, you need a data set. You need to register a data set to start with, okay? So we have data sets here under the assets. I can register our data set from here. I already registered the heart disease data set. Actually, I get it from here, from a website called Kaggle. This is a data science website where you can practice and actually participate in competitions related to the machine learning and data science field. This is the data set about heart disease, and it's an Excel or CSV file. I uploaded this data here from the local file. I downloaded from Kaggle. Then once it's registered, you can explore it directly from here. This is Explore. This is how it looks like. Okay, we have age, we have male or female, we have male chest type, vein type, and so on. If you want to understand the definition of each field here, you can go to Kaggle, and Kaggle provide you with a description for each field, okay? As you can see here, okay? This is a way to understand the specific data set in that case. So we register the data set. Why we need to register the dataset? Because actually registering the dataset will make this registered dataset available across the whole workspace. It gives also the privilege of versioning your dataset. It gives also the power of changing the schema or the data itself and keep track of these changes. It gives also the benefit of tracing the trend models against the version of the data that you have used during the training phase. It's a really awesome thing to have this feature because it's provide you with a lot of benefits either during the data preparation or during the training of the model, or later when you want to check the changes in the data over time, if you want to compare any drift happen in this data and so on. I also created here a profile for this data. Data profiling means as part of exploratory data analysis, EDA, we try to understand the distribution of the data, okay? How each variable, how each field here is distributed, okay? I can understand that maybe this distribution is skewed to the left side or the right side in the lower values range or in the upper values range, but eventually it gives you an idea about your data, and you have to understand your data before jumping to the training, okay? Because if you don't have the right data and you trained your model against this maybe rubbish or unprepared data, you will not get a good results at the end, okay? So as you can see, we have histograms for the distribution of each field here under the data profile. This is also a very nice feature, okay? And we can also have consume here. Consume tab will show you how to consume your data using Python script as a boilerplate code, okay? This is also a nice thing to save your time with the common tasks, which doesn't need a lot of thinking. You have to focus on your problem. So this is also given if you want to use it from here. This is about the data. Back to the AutoML, I will use this heart disease. So I'll start a new automated ML run. Once I click here, I start from picking which data I'm going to use. We said heart disease data set, and next. We actually can submit our data into an existing experiment, as we explained about the experiment before, or create new one. So just for sake of time, I will create, I will run this experiment, within the existing experiment, which is called AutoML heart disease, okay? What is the target column? What is the final outcome of this? If the patient has heart disease or not, okay, based on the inputs. So the target column called target, it's an integer, 0 or 1. If 0, the person doesn't have heart disease. If it's 1, so most likely this person has heart disease, okay? And he within the suspicious group that need to have more diagnosis or more focus or care, okay? So we have the target. And as we said, every experiment need a compute, a virtual machine, a cluster to run on. I have here one compute cluster called compute cluster, dash cluster, which I created before. Then next, now you can use the AutoML instead of building things from scratch. AutoML, automated ML, will help you actually, but you just need to pick the right parameters, the right selections. Our task here, based on the definitions we explained before, is it regression or is it classification? It's a classification because we have two discrete outcomes, yes or no, patient or not, and it's a classification problem. So I will pick classification. I can use classification deep learning neural network models if I want, but for the sake of this simple problem, I don't need it. So I'm not going to enable that. Then I have also the option of extra configuration. So let's see it here. You can decide about which evaluation metric you are going to use. So you have, if you remember, we have accuracy because it's a classification problem. And we have precision, we have recall, we have many other metrics for the evaluation of this classification problem, like area under the curve, AUC, okay, area under curve. And we have something called norm macro recall, which is another extension of the recall that we discussed. And we have the precision, we have something called average precision score. There are many metrics. We are going to pick accuracy here. And you have also one feature here, which is explain best model. So the AutoML will go across different models, try all of them, and finally will get with the best accuracy for a specific model, the model with the best accuracy as the final one. And if I want to understand more why the automated ML service pick a specific model, I can go and see something about more explanation for why this model is the best out of 10 models or 100 models. I can here also block some algorithms. Suppose the automated ML gives me 20 different algorithms I can select from, but I want to focus, based on my experience, I want to focus on a specific algorithms. Like, for example, I can block all of the algorithms and just focus on the random forest or XG boost classifier, okay? This where you can block the algorithms you want to exclude, and you can define also the exit criteria. This exit criteria could be how much time you want to run this experiment, okay? This experiment run. I can put 3 hours, 1 hour, maybe I want to run it only for 15 minutes. And I can also specify the exit criteria based on the score. We select the metric as accuracy. So this accuracy is something from 0 to 1. In that case, I can decide, okay, if during the experiment, in the execution, if you get 80% or above, this is a good thing for me, and you can exit the experiment run, okay? Also, the validation here, this validation could be using different methods. In that case, we can just rely on train validation split, the most easy common way, okay? And we have concurrency. This train validation split will split your data into 2 sets, one for training and another for validation or testing. Here, you can specify the percentage. How much of your data you want for testing, you want to keep it for testing, and how much for training. Definitely, because it's 2 sets. If I said percentage of validation data set will be 10%, so automatically the training data set will be 90%. And the concurrency here, if I'm running different iterations against different algorithms, may I decide to parallelize these executions into parallel iterations or parallel executions at the same time to save time, but that actually needs to have enough resources to get faster execution. Okay. Once I'm done with this, I'm going to save. And also I can play with something called featurization setting. In the featurization setting, you see all of the features you have in your data. And if you notice here, all of them are features except the outcome, because this is the target. Okay. And in the feature type, you can change the type of the feature itself. By default, it's numeric. But if I decided that for some reason, no, I believe I have this feature or this column as a categorical where I have different values, but it's very discrete values. Like I have 50 values. I have USA states, and I give a number to each state from 1 to 50. Okay. And instead of dealing with these numbers as a numeric, I will deal with it as categorical. I will consider each one of them as a different category. This is another way of thinking, okay? And imbued here means if I find missing values, how to deal with this missing values within this variable? Shall we remove the row which has missing value? Shall we drop the column that has missing value? Shall we change the missing value or the empty value, for example, with the mean or the median of the row or the column? All of these different settings that we can pick from, okay? This is the featurization. Once we are done, we can finish, and this finish start creating a new automated ML run. It runs for some time. Once it's done, it will show something like this, which I already ran before here. I have this run, which is completed. And then this run, actually, I get this nice model. This is the final model which I get. This model actually has 82% accuracy. Okay, and if I go deeper, I can see that this model, which I get it from the automated ML, I can right away from here deploy it to Azure Kubernetes service or a specific compute. I can pick from here, and I already deployed this just to save time. So if I go here, I deployed this model as an endpoint, as a web service. You can see it here called heart disease prediction. Go to this endpoint. Within the endpoint, you can see the metadata about the endpoint, and if you go to the test, you can see the URL. You can see actually the interface where you can test this data, this endpoint or this web service to get predictions. And we have also another tab called consume. This consume give you a boilerplate code in Python, in R, in C#. You can copy this, and this is the URL of your web service. This is a REST endpoint URL. And this is the authentication primary key you can use to authorize yourself while consuming this web service. And I have here a notebook where I copied this code for consuming our web service. In this notebook, if you go, you can test from here. I have something called test. Here I have, this is a notebook we can create here. Okay, so I can go and create my Jupyter notebook where I can take the boilerplate code, just execute it from there, just to see the predictions. So create new file. I will choose a file type as a notebook, and I'll give it a name. Let's call it test heart predictions. Create. That we create an empty notebook. In that empty notebook, that boilerplate code. Let me save this. Get this Python code from here. Copy. Go to the notebook again. Just paste it here. I will just clean up a little. These things I don't need. I have sample data. This sample data I can actually provide here to get predictions. Okay, so this is a way of getting predictions. You can play with change this data here right away in the notebook, and then with this simple code you can get the prediction of this model. So your model is encapsulated somehow as a web service. You are not dealing with any much details except the web service URL and the keys where you authenticate your access to this service. Okay, this is a way of thinking. We have also, just for the sake of time, in summary, the other example for the designer where we have the training pipeline and the inference pipeline. I have here one pipeline called diabetes training pipeline. Let's open it to see what's inside. This is the designer we talked about, where we build our training pipeline. If you notice here, we have the toolbox, and let me explore this one that I have built for you for today's demo. I start from the data set itself, which I registered before, as we said, and then I run a module called summarize data to get a statistical summary about my data, to understand the distribution of the data and the histogram and I have outliers in the data I need to deal with, all of these aspects. And also I have something called filter-based feature selection. In the filter-based feature selection, we try to apply here something called Pearson coefficient or Pearson correlation. Okay, this Pearson correlation will measure the linear correlation between the input variables and the outcome. This will give me an idea about if I have a strong linear correlation either in the positive direction or negative direction between specific variables in my data and the final output. This means that these features or these variables are the most important data which I have to train my model on. I find very weak correlation between some specific variables in my data with the final outcome, which means this weak relationship means that I can even drop these variables from training phase because it will not help a lot. It's not that important while training my model. This is a step where we are doing this. I select here that I operate on feature columns, and my target is the outcome field. Number of desired features 5. So here, this module will pick the most important 5 desired features, which is highly correlated with the outcome. Okay. After this selection of the most important features based on the correlation, as we said, we have normalize step where we can normalize our data. We said before, the normalization means if we have big variance on in the scale of our input data, we can put all of them on a common scale, because usually the things which has big values will dominate the other variables or the other features which has smaller numeric values. This is very common in the machine learning models, and we have to solve this problem by normalizing the data. Normalizing the data here means make them on a common scale. In my case, I use the transformation method as min-max. Min-max means simply make those fields or those columns on the scale from 0 to 1. Okay. After that, I get the normalized data. I'm done with the pre-processing and preparation step. I'm going to the split data. In the split data, I'm splitting my data into 2 sets, one for the training, another for the validation. Here, I choose to make it 80% for the training, 20% for the validation. And then I goes to train model. This module expect 2 inputs. I have the training data itself and which algorithm I'm going to use here to train my model. I have 2 algorithms because I'm training 2 different models here. On the left side, you can see something called logistic regression. This is a classifier. Okay, this logistic regression is an algorithm I can use for classification problems. Okay, and I'm putting this logistic regression algorithm as an input for the train model, and I'm putting also the train here, the training dataset. This train model will train, and also I have, as I said, a second algorithm called two-class decision forest. It's a decision forest. This decision forest, it's a group of decision trees, and it's an input also for this train model here. We are training these two models in parallel. This execution graph will be highly optimized when it's running. And if there is no dependency at all between these specific blocks in the pipeline, it will not run sequentially. It will run in a parallel mode, okay? Just to make effective processing for the execution graph of the pipeline. Then, once we have the models trained, I have two models. I want to compare both of them, which one is the most effective one, the best model. Then I take from the split here, the validation set or the test set, I feed it here into the score model. This is score model to score the first model on the left. The second score model is to score the second model on the right. I get the scores from the validation set or the test set. These scores, I can evaluate both of them. And from here, I can see which model is the best, which model is the best model, which I can pick as a final model for the inference or the prediction. This is the total, the different blocks within our pipeline. And we try actually to correlate these steps with what we mentioned about the machine learning steps, okay? Because this is the typical steps. Now, we have another pipeline for the inference called diabetes inference pipeline. This is a prediction version of the trained pipeline, okay, training pipeline, where I'm actually using the trained pipeline to produce predictions from this trained model. This trained model is registered here. See, this one called diabetes model, this model is registered here. And by the way, you can run it from here, you can deploy it also from here and create a web service based on that model. And also you can download the model itself in something called Beckel format. This Beckel format is a very common format in the machine learning models, where you can take this trained model and use it somewhere else to make it portable, okay, and so on. Back to this designer, this pipelines, we can see this inference, okay, this inference pipeline. It's all about web service input to apply some transformations, which we talk about, like normalization and so on, then scoring the model. Now we don't have a training anymore. We are done with the training. Now we are talking about the real-time inference. So it's all about using the trained model to make scoring, okay? And then get the output, which we call it web service output. This is the graph of the execution for the inference. Now, this inference pipeline, we can deploy it as an endpoint, which is this one. I already deployed from here, and it's called Diabetes Prediction Service. This Diabetes Prediction Service, I can test it from here. I have the different features, different inputs. Those inputs, if I test, I can get the results. The result here is the score variable 1. 1 means that this person is diabetic, okay, based on the given data. So now we are getting predictions from our model. And we have something also called scored probability. The scored probability is 61%, about 61%. What does it mean? It means that 60% it's a diabetic patient, and the remaining percentage is non-diabetic. So the model is more confident that this person is diabetic with this 61%, and may still have a little probability or a little percentage that this person is non-diabetic. So this is how to see the final outcome, and this is a way to see the outcome. However, you are not limited to this, as we said, because you still have the consume, and you can get this web service as an AI developer or machine learning engineer. Take this web service, give it to any other developer who can make use of it without even understanding what is the details of this model. He doesn't need to understand anything about these techniques or different algorithms for machine learning. You just need to take this web service and take the authentication keys and then deal with it like any normal web service to consume it and to get specific results or specific predictions. That's it for the prediction part or the inference part. Same here, we have boilerplate code for this thing as well. And I have already here this notebook. Actually, if we go, I have another notebook I have created before, Jupyter Notebook, to test the diabetes prediction. This actually, we can see it here also in Jupyter or Jupyter Lab, where you can see it in a more extended view. Here in this extended view, you can see the normal Jupyter Notebook. And this is our boilerplate code. You actually can execute that here, okay? Just run or control enter. That actually directly get the input you give to the service, hit the service, score the inputs using the trained model, and finally get the result of your predictions. And this is actually almost the same shape of results we get when we used the other way of testing for this specific model. This is actually summarizing. The two demos we prepared for today. I have another more advanced techniques to tune the same model in Azure Machine Learning Designer, okay? But I don't think that we have enough time for this, but just for sake of just view what we have in the tuned version of the same model, I have here the tuned version of the model. You can see that it has more details here, or I would say instead of train model, we replace this with something called tune model hyperparameters. And in the tune model hyperparameters, each algorithm has multiple setups. It's not a single setup. These are the hyperparameters we talk about, because in the hyperparameters, whenever I change the algorithm, the parameters of the algorithm itself, it considers a new variant of this algorithm, a new variant of this model, and so on. Okay. So, for example, you have in the decision forest, one of the hyperparameters is the number of decision trees. I can ask the model to be trained against 1 decision tree, 8 decision trees, 32 decision trees. And these different combinations, we can try all of them or try random sample of them. And finally, the tune hyperparameter, model hyperparameter model here will be able to come with what we call it the best model. We can come with the best model here. If you look, this is a visualization where you can see what is the best model across the different runs when we try different hyperparameter values for this specific algorithm. And you can get from here the trained model. And by default, if you have multiple models have been trained, by default, this module for tune model hyperparameters will give you the best model of them based on the evaluation metric you have decided. And then you again score and evaluate as usual, as we saw that before. And this is also a kind of variation of the same pipeline, but in that case, we created different setup for our algorithm in the training phase to see which better values we can give to these hyperparameters to enhance the accuracy or the efficiency of our model. Okay, and as we can see here, the notification came for our automated ML run has been completed, where we can see the final output, and the final output by default will be that we get actually multiple models here, and by default the model at the top is the most better model or the best model with accuracy of 83%. Okay, and we can right away from here, as we said, get the model and deploy it as an endpoint or as a web service. Here also we have the compute that we actually discuss. We have something called a compute instance, where you have one single instance for development to run your Jupyter Notebooks. Here you have compute clusters where you have multiple nodes to train your training pipeline, to execute your training pipeline against. And you have the inference cluster. This is our mini AKS cluster, which I deployed, by the way, our endpoint too. So our endpoints that we just tested now, it's already deployed to this inference cluster on mini AKS. And this attached compute is all about if you bring your own compute, if you have other virtual machines, which is not part of the machine learning workspace, but you want to use it as part of the compute resources we have in this machine learning workspace, you can bring it to the workspace and register these external computes here. Okay, this is also available here in the workspace. With that, I think we covered all of the topics and all of the details we planned for today. Sorry for the extra time, but I really was keen to make sure that you get the best out of this session. Thank you so much for staying with us till that time. And in 2 or 3 minutes, if you have any questions, please feel free to post them. Let me check first if we have any. Yeah, we have one question here. Okay, let me publish this question for everyone to see. How to automate model retrain in Azure when existing model is outdated? Yeah, here you are talking about you have already a trained model, and this trained model is outdated, maybe because of data drift, or over time we have changes in the distribution of the data, and we want to automate the retraining of this model. Actually, you can do this, but you will be limited to specific configurations because you will rely on the automation pipelines. For example, you can go and automate the pipeline and make this pipeline as a training pipeline execute based on a specific events or based on a specific schedule. Or even better, you don't need to automate or schedule this training pipeline on a specific schedule or a specific interval, but instead of that, you can use one feature in Azure machine learning service called data drift detection, and this data drift detection will notify you whenever, while monitoring the deployed model in the production environment, if there any degradation in the performance or any detected drift in your data which cause this kind of degradation in the performance. This is also another option, but yes, you can automate the model retraining, but in all cases, during the automation, someone should be there to check the results and evaluate and compare between the different models, and maybe you need to further fine-tune your hyperparameters in the model, as we said. So, but as a general answer, yes, you can do that. And as we said, if you remember, we said we can utilize the DevOps practices to get the same concept for CI/CD pipeline within the machine learning. And as you might know, there are something called MLOps, which is a variation of the DevOps, but in the machine learning field, can also make use of these practices to automate the retrain of your model in case you have any problem with your current model, which is used in the production environment. I hope that answers your question. So as I can see, we don't have any other question except that one that we answered. Thank you so much for your time, and I hope you enjoyed this session. And we have another session next week on Wednesday about Python SDK in Azure Machine Learning Service and how to go and build your own pipelines and machine learning models and deploy them programmatically from the Jupyter Notebook using the Python SDK. Thank you so much, and have a great night. Bye-bye.